May 14th, 1942. Corregidor Island, Manila Bay. Lieutenant Commander Yoshio Takahashi knelt beside the twisted wreckage in the pre-dawn darkness, his flashlight beam catching the dull gleam of metal beneath layers of tropical dust and battle damage. The American SCR-270 radar set lay before him, half buried in rubble from the bombardment that had finally broken the fortress's resistance 3 days earlier. Parts of the antenna array were shattered, but the transmitter housing remained largely intact, its copper components visible through a rent in the steel casing. What Takahashi held in his hands at that moment would explain a mystery that had been costing the Imperial Japanese Navy aircraft and ships since the war's opening months. The Americans and British possessed detection capabilities that seemed to violate the known limitations of radio technology. Japanese bombers approaching targets were being intercepted before they arrived. Surface ships were being engaged at night in weather conditions where visual detection should have been impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Most disturbing of all, the ranges at which these detections occurred exceeded anything Japanese engineers believed technically feasible. The psychological dissonance had begun months earlier, but until this morning on Corregidor, no Japanese officer possessed physical proof of what Allied technology had achieved. The captured radar set represented more than damaged equipment salvaged from a defeated fortress. It embodied a technological reality that would force Japanese scientists and military commanders to confront an uncomfortable truth about the electromagnetic war they had been fighting blind. The device before Takahashi operated at wavelengths Japanese radar developers had largely abandoned as impractical. It generated detection ranges his superiors would dismiss as exaggeration or measurement error. Yet here it sat, real and tangible, waiting to be dismantled and understood. Commander could not have known that this single piece of captured equipment would become the centerpiece of Japan's most intensive radar analysis program, or that the findings would reveal not just a technological gap, but a fundamental failure in Japanese understanding of what modern warfare required. The story of how Japanese forces came to examine this radar, and what they discovered, begins not on Corregidor, but in the command centers and laboratories of Tokyo, where in the years before Pearl Harbor, Japan's radar development had taken a path that would prove catastrophically inadequate for the coming conflict. Throughout the 1930s, Japanese scientists had demonstrated remarkable early progress in radar technology. Professor Hidetsugu Yagi, whose pioneering work on antenna design in the late 1920s had been studied by researchers worldwide, represented Japan's potential in this emerging field. The cavity magnetron that Japanese researchers produced in 1937, generating microwave frequencies at 10 centimeters wavelength, actually preceded comparable British developments by several years. In 1939, Japan Communications Company built a 10-centimeter, 500-watt cavity magnetron that represented genuine technological leadership. Yet this early promise never translated into operational capability. The disconnect between laboratory achievement and military application in Japan reflected institutional failures that would plague the nation's war effort across multiple technologies. The Army and Navy maintained separate, competing radar research programs that rarely shared information or coordinated development efforts. Within each service, multiple organizations pursued overlapping projects, fragmenting already limited resources and technical expertise. When Yanagimoto Ryusaka, chief of the Navy General Staff's Armaments Section, insisted in 1941 that the Navy could not go to war without radar, his warning prompted a crash development program launched on August 2nd, 1941. But even this belated urgency proved insufficient. By August 1943, the Navy's Electrical Research Department, responsible for all radar development, had grown to just 300 staff. For comparison, America's Radiation Laboratory at MIT employed over 1,000 scientists and engineers working exclusively on microwave radar systems. The resource constraints extended beyond personnel. Japanese industrial capacity, already stretched by simultaneous campaigns across the Pacific and Asia, could not support the massive production scales required for widespread radar deployment. Quality control deteriorated throughout the war as material shortages worsened. By 1945, only one vacuum tube in 100 actually worked upon manufacture, and even those passing inspection failed within 100 hours of operation on average. For radar sets requiring 40 tubes, this meant a mean time to failure of just 2 or 3 hours, rendering the equipment effectively useless for combat operations. The shortage of nickel used in vacuum tube heater filaments became so severe that Japanese procurement officers were reduced to purchasing nickel coins in Hong Kong and melting them down for raw material. This represented the material reality facing Japanese radar development, a reality of scarcity and improvisation that contrasted starkly with Allied industrial abundance. But the most damaging failure was conceptual rather than material. Japanese military leadership never fully appreciated radar's potential to transform warfare. Early experiments with Doppler interference detectors for aircraft detection proved disappointing, and these technical dead ends reinforced institutional skepticism about radar's utility. The technology remained viewed as interesting but marginal, useful for specialized applications, but not essential for victory. This attitude persisted despite mounting evidence from the war's opening engagements. During Japan's initial offensive operations in December 1941 and January 1942, Japanese forces encountered radar installations at various captured locations. At Singapore in February 1942, advancing Japanese troops discovered the damaged remains of British Good Luck Mark II radar and a searchlight control radar. The equipment was badly damaged, but Japanese technicians recovered a set of handwritten notes containing details of the SLC's theory and operation. These early captures provided tantalizing glimpses of Allied capabilities, but the damaged state of the equipment limited what could be learned through examination alone. Japanese engineers could see that the British had developed operational radar systems, but without functioning examples to test, they could not fully appreciate the performance characteristics or understand the principles enabling the ranges Allied forces were achieving in combat. The situation changed dramatically with Corregidor's fall in May 1942. American forces defending the fortress island had fought with desperate courage for months, enduring constant bombardment and steadily tightening encirclement. When General Jonathan Wainwright finally ordered the garrison's surrender on May 6, 1942, Japanese forces occupied facilities that had been hastily but incompletely destroyed. Among the captured equipment, search teams discovered 2 American radar sets that would prove invaluable for Japanese technical intelligence. An SCR-268 anti-aircraft fire control radar sat in operational condition, its circuitry intact despite the chaos of the fortress's final days. The SCR-270 early warning radar that Lieutenant Commander Takahashi examined had sustained significant damage, but enough remained to allow detailed analysis of its design and components. The SCR-268, operating at 205 MHz with the wavelength of 1.5 meters, represented mature American radar technology from the late 1930s. The system could detect aircraft at ranges up to 22 miles and provide sufficiently accurate directional information to control anti-aircraft searchlights and guns. For Japan, which had captured no functional Allied radar systems before Corregidor, the intact SCR-268 provided an unprecedented opportunity for reverse engineering. But it was the damaged SCR-270 that would prove most revealing, because this system embodied capabilities that Japanese engineers had dismissed as impractical. Operating at 106 MHz with a wavelength of 2.83 meters, the SCR-270 could consistently detect individual aircraft at ranges exceeding 125 miles. Formation flying generated radar returns detectable at ranges approaching 240 miles. These figures far exceeded anything Japanese radar development had achieved or even attempted. The combination of long wavelength operation and extreme detection range violated Japanese understanding of radar physics. Conventional wisdom held that longer wavelengths produced weaker returns and shorter detection ranges. The mathematics seemed straightforward. As wavelength increased, target cross-section decreased proportionally, reducing the strength of reflected signals. Yet the Americans had somehow achieved extraordinary range, using relatively long wavelengths that should have limited performance. In rare coordination between competing services, the Imperial Japanese Army and Navy jointly organized technical teams to examine the captured equipment. The significance of the find overcame normal institutional rivalries. Both services recognized that understanding Allied radar capabilities had become essential for combat effectiveness. The examination would be conducted at the newly formed Tama Technology Research Institute, which the Army established on June 11, 1943 to consolidate radar development efforts. The technical teams faced immediate challenges in their analysis. The SCR-270's damage meant they could not simply power up the system and measure its performance. Instead, they had to reconstruct its capabilities through detailed examination of components, circuit analysis, and theoretical calculations based on the physical design. The process required weeks of painstaking work as Japanese engineers disassembled, measured, photographed, and attempted to understand every aspect of the American radar's construction. What they discovered astonished them. The SCR-270's transmitter generated 100 kilowatts of pulsed power, far more than any Japanese radar system produced. The massive antenna array, measuring approximately 15 feet high and 70 feet wide, collected reflected signals with efficiency Japanese designs could not match. The receiver circuitry demonstrated sophisticated signal processing techniques that improved detection of weak returns from distant targets, but raw specifications told only part of the story. The American radar's operational concept differed fundamentally from Japanese approaches. Where Japanese systems prioritized accuracy over range, focusing on precise target location for fire control applications, the SCR-270 sacrificed directional accuracy to achieve maximum detection distance. Its purpose was early warning, providing sufficient advance notice for defenders to prepare interceptors and position defenses. The philosophy reflected an integrated approach to air defense that Japan's fragmented command structure had never developed. Captain Hiroshi Matsumoto, chief engineer at the Navy's Technical Research Facility at Yokosuka, and filed a classified report in July 1942 that captured the cognitive dissonance Japanese technicians experienced. "The American radar achieves detection ranges we calculated impossible," he wrote. "Our analysis of the power, output, antenna gain, and wavelength characteristics suggests maximum useful range of approximately 50 miles for targets of known cross-section. Yet intelligence reports and the device's own design parameters indicate operational ranges exceeding 100 miles routinely, with maximum detections beyond 200 miles. The report continued with a note of professional bewilderment. "We request additional time to verify our measurements and calculations. The discrepancy between theoretical performance and reported capability suggests either errors in our analysis, misunderstanding of operational parameters, or technologies we have not yet identified. Without functional test data, we cannot resolve these contradictions with confidence." The contradiction Matsumoto identified pointed to a fundamental gap in Japanese radar understanding. The Americans had achieved their remarkable ranges not through revolutionary physics, but through engineering excellence in areas Japanese development had neglected. Superior power generation, more efficient antenna designs, advanced receiver sensitivity, and sophisticated signal processing combined to push detection capabilities far beyond what simple calculations suggested possible. But perhaps the most significant finding was what the examination revealed about American industrial capacity. The SCR-270 was not a laboratory prototype or specialized equipment reserved for critical locations. It was production hardware, manufactured in quantity and deployed widely across American defensive positions. The engineering tolerances, component standardization, and construction quality all indicated mass production rather than hand-built prototypes. By December 7, 1941, 112 SCR-270 and SCR-271 systems had been manufactured and deployed, with more in production. This realization carried profound implications. Japan faced an enemy that could not only design advanced radar systems but produce them in quantities that allowed widespread deployment. The gap was not merely technological but industrial. Even if Japanese engineers could match American radar performance through copying or parallel development, Japanese factories could never manufacture systems at the scale required to field them throughout the expanding defensive perimeter Japan was attempting to hold. The examination of the captured equipment also revealed American attention to operational practicality. The SCR-270 was designed for mobile deployment, with components that could be transported by truck and set up at new locations relatively quickly. Power requirements, though substantial, could be met by portable generators. The operators required training, but the controls were logical and the displays straightforward. These design choices reflected mature development processes that prioritized fielding working systems over achieving theoretical perfection. Lieutenant Commander Yuji Yamamoto, assigned to coordinate Army-Navy analysis efforts, wrote a memorandum in August 1942 that acknowledged the scope of what Japan faced. The captured American radar systems represent not isolated technical achievements, but evidence of systematic development supported by substantial resources. The quality of components, sophistication of design, and attention to production manufacturability all indicate programs far more extensive than our own efforts. Most concerning, these systems were in widespread deployment before hostilities began, suggesting development timelines of several years, supported by funding and personnel allocations we have never approached. The psychological impact of these findings rippled through Japan's technical community. Engineers who had been confident in Japanese technological capabilities now confronted evidence that in radar development, Japan had fallen years behind, despite early theoretical advantages. The cavity magnetron that Japanese researchers had pioneered in the 1930s had never been developed into operational systems, while British and American magnetrons powered radars that were deciding battles across the Pacific and Europe. Captain Matsumoto's follow-up report in September 1942 attempted to quantify the gap. Conservative estimates suggest American radar capability exceeds our own by a factor of 3 to 5 in detection range, accuracy, and reliability. More concerning, their apparent production capacity suggests they can field radar systems at rates we cannot hope to match. Intelligence reports indicate radar installation on ships, aircraft, and fixed installations across their defensive network. By contrast, our radar deployment remains limited and concentrated at major facilities. The report concluded with a stark assessment. Closing this capability gap will require resources beyond our current allocation. Even with increased funding and personnel, matching American technical capability appears unlikely given our industrial limitations. We recommend focusing development on specific applications where radar provides maximum tactical benefit, rather than attempting to match American capabilities across all domains. This recommendation reflected a painful acceptance of Japan's limitations. The vision of comprehensive radar coverage, providing early warning and fire control throughout Japan's defensive perimeter, was recognized as unattainable. Instead, Japanese radar development would focus on specialized applications, accepting that Allied forces would maintain overwhelming advantage in this crucial technology. But the most significant revelation from the Corregidor captures remained the detection ranges. Even as Japanese engineers understood the technical means by which American radars achieved their performance, the psychological adjustment to operating against enemies who could detect approaching forces from distances exceeding 100 miles proved difficult. Combat doctrine, operational planning, and tactical procedures all assumed detection ranges measured in tens of miles at most. The reality that American forces routinely detected Japanese formations at ranges where interception and defense could be coordinated effectively rendered many Japanese tactical approaches obsolete. This would prove especially devastating for Japanese aviation. Bomber formations approaching targets with radar warning could be intercepted by defending fighters scrambled with sufficient time to gain altitude advantage. The element of surprise that had been central to Japanese operational planning vanished when radar could provide defenders tens of minutes of advance warning. Strike coordination that assumed defenders would have only brief warning before attack instead gave opponents extended preparation time. The examination of captured radar equipment at Corregidor revealed to Japanese technical experts what their combat forces were already discovering through bitter experience. Japan was fighting an electromagnetic war where the enemy possessed capabilities to detect, track, and engage forces at ranges Japanese equipment could not match. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The mathematics and physics were now understood. The engineering principles were documented. The specifications were measured and recorded in technical reports. But understanding the problem provided no path to solving it. Japanese industry could not produce radar systems matching Allied performance at anything approaching the scales required. Japanese scientists and engineers possessed the knowledge to design advanced radars, but the fundamental constraints of industrial capacity, material availability, and resource allocation meant this knowledge could not be translated into deployed capability that would affect the war's outcome. Captain Matsumoto included a final observation in his October 1942 assessment that captured the essential futility Japanese radar development now faced. We have examined the enemy's technology and comprehend how it functions. We understand the principles and could replicate the designs, given sufficient resources and time, but we also understand that even successful replication would not close the gap. By the time we field systems matching current American capabilities, they will have advanced further. We are chasing a target that moves faster than we can follow. The frank admission represented a professional assessment untainted by propaganda or wishful thinking. Japanese engineers examining Allied radar technology understood they were witnessing not just technical superiority, but the manifestation of industrial and organizational advantages Japan could not overcome through cleverness or determination alone. The captured equipment provided answers to technical questions about how Allied radar functioned. It provided no answers to the strategic question of how Japan could prevail against enemies with such decisive technological and industrial advantages. Yet the examination continued, and Japanese engineers persisted in their efforts to develop indigenous radar capabilities. The knowledge gained from captured equipment informed new development programs. Based on the SCR-268 examination, Japanese contractors produced the Tachi-1 and Tachi-2 radars, operating around 200 MHz and incorporating techniques copied from the American system. Sumitomo Electric produced approximately 65 units total, before switching production to the Tachi-3 based on captured British Good Luck Mark II radar. These derivative systems entered service in 1944, nearly 2 years after the examination of the captured American equipment. By then, Allied radar technology had progressed to microwave systems based on cavity magnetrons, operating at 10 cm wavelength with superior range and accuracy. The Japanese radars entering service in 1944 were already obsolete by the standards of equipment. Allied forces were deploying. The Japanese Navy achieved somewhat better results with its Type 22 radar, a 10 cm microwave system that entered service in September 1944. Operating at 2 kW peak power, the Type 22 could detect aircraft groups at 35 km and single aircraft at 17 km. Surface ships could be detected at ranges approaching 35 km. The system demonstrated that Japanese engineers could design and produce microwave radar systems approaching Allied capability. But only 300 Type 22 systems were built during the war, reflecting the production constraints that limited Japanese radar deployment regardless of technical capability. By mid-1944, most major Japanese warships carried Type 21 or Type 22 radar, but coverage remained spotty compared to Allied forces, where even patrol boats carried radar systems. Destroyers typically mounted 1 or 2 radar sets depending on their role. Larger ships carried multiple systems for air search and surface detection. The quality control issues that plagued all Japanese electronics production affected radar systems severely. Vacuum tube failures rendered sets inoperative for extended periods. Replacement parts were difficult to obtain. Maintenance required skilled technicians who were increasingly scarce as the war progressed. Systems that worked effectively when first installed degraded rapidly under operational conditions, reducing the already limited radar coverage available to Japanese forces. The strategic impact of Japan's radar inferiority manifested in countless engagements throughout the Pacific War. At the Battle of Midway in June 1942, Japanese carriers lacked radar warning of approaching American dive bombers. Visual lookouts provided the only air defense, giving defenders insufficient time to position fighters effectively. The devastating attack that destroyed 3 carriers in minutes succeeded in part because radar could not provide the early warning that might have allowed effective fighter direction. In the Solomon Islands campaign beginning in August 1942, Japanese naval forces conducting night bombardments of Guadalcanal's Henderson Field were repeatedly surprised by American forces using radar-directed gunnery. The Battle of Cape Esperance in October 1942 saw American cruisers detect Japanese ships at ranges where Japanese lookouts could see nothing, enabling the Americans to achieve complete tactical surprise despite Japanese superiority in night combat doctrine and training. The examination of captured radar equipment had explained to Japanese technicians why their forces were suffering these defeats. The understanding provided no remedy. Japanese ships without radar operated blind against enemies who could detect them at extended ranges in any weather or lighting conditions. Japanese aircraft approaching radar-equipped targets faced prepared defenses scrambled with sufficient warning to establish advantageous positions. Japanese ground forces at radar-equipped installations could track approaching threats when Japanese attackers were still beyond visual range. The technological asymmetry shaped operational planning on both sides. Allied forces could conduct operations confident their radar would provide tactical advantages in detection and engagement. Japanese forces had to assume Allied radar coverage and plan accordingly, accepting that surprise would be difficult to achieve and that defending forces would have extended warning. These constraints limited Japanese operational options and forced attacking forces to accept unfavorable tactical conditions. By 1944, American B-29 bombers conducting strategic raids against Japanese home islands carried jamming equipment that blinded Japanese radar systems, attempting to direct defensive fighters. The APR-4 intercept receiver, carried by 1 in 4 superfortresses, allowed dedicated Raven operators to detect Japanese radar emissions and coordinate jamming responses. Active jamming systems proved brutally effective, completely overwhelming Japanese radar capability. Interrogations of Japanese radar operators after the war revealed the psychological impact of this electronic warfare. Operators described seeing their scopes overwhelmed with false returns when American jamming activated. The carefully trained techniques for identifying genuine targets from clutter became useless when jamming created screens full of spurious returns. Defensive operations that depended on radar direction collapsed when operators could no longer distinguish actual bomber formations from jamming signatures. The collapse of Japanese radar-directed air defense represented only the most visible manifestation of a deeper technological failure. By early 1945, the accumulated effects of radar inferiority had fundamentally altered Japan's strategic position. The examination of captured Allied equipment 3 years earlier had revealed the nature of the problem. 3 years of desperate effort had failed to solve it. Lieutenant Takeshi Yamada experienced this failure personally during his final combat sortie on March 9, 1945. Flying a Kawasaki Ki-45 night fighter from Chofu Airfield near Tokyo, Yamada had been scrambled to intercept a formation of B-29 seconds conducting a low-altitude incendiary raid on the capital. The ground control intercept station had detected the American bombers approaching, but the Type 4 Mark I Model 2 airborne radar mounted in Yamada's aircraft proved nearly useless for locating individual targets within the massive formation. The radar's maximum range of 4 kilometers meant Yamada had to maneuver his fighter dangerously close to the bomber stream before detection became possible. Even then, the primitive display showed only a vague indication of direction, providing insufficient information for an effective interception approach. Yamada spent 40 minutes searching the night sky visually, his radar offering little assistance, while below him Tokyo burned with an intensity that turned night into flickering orange day. He finally spotted a B-29 silhouetted against the fires, attacked from below, and saw his 20mm rounds strike the bomber's wing root. The superfortress continued flying, its self-sealing fuel tanks and robust structure absorbing damage that would have destroyed a Japanese bomber. Before Yamada could position for a second attack, the B-29's tail gunner found his fighter with radar-directed fire. Tracers walked across Yamada's canopy. He broke away, his aircraft damaged, and returned to Chofu having achieved nothing except survival. The raid killed over 80,000 people in a single night. Yamada's ineffective interception typified the Japanese night fighter force's experience throughout the strategic bombing campaign. The Americans flew with radar that allowed bombardiers to identify targets through clouds and smoke. They navigated with radar that made night navigation as precise as daylight. Their gunners aimed with radar fire control that could track and engage targets in complete darkness. Japanese defenders possessed radar systems that barely functioned, operated unreliably, and provided information too crude for effective combat employment. The industrial data underlying this disparity tells its own story. By war's end, American industry had produced approximately 30,000 radar sets of various types. Japanese industry, despite beginning with comparable scientific knowledge, produced approximately 6,000 radar systems total. The numerical advantage of 5-to-1 understates the true gap, because American radar systems were generally more capable, more reliable, and better integrated into operational doctrine than their Japanese counterparts. The examination of captured Allied radar had given Japanese engineers detailed knowledge of enemy capabilities as they existed in 1942. This knowledge proved insufficient to close the gap because the gap was never primarily technical. The fundamental constraints were industrial and organizational. Japan lacked the manufacturing capacity to produce radar systems at scale. It lacked the organizational structures to coordinate development across competing service branches. It lacked the resource base to support radar production while simultaneously supporting aircraft production, warship construction, and the myriad other demands of a global war. Captain Matsumoto's assessment from October 1942 had proven prophetic. Japanese engineers could replicate Allied designs. They could not produce them in sufficient quantity or quality to affect strategic outcomes. Understanding the enemy's technology provided no path to matching it when the underlying industrial and organizational foundations were inadequate. The post-war interrogations of Japanese radar personnel revealed the human dimension of this technological failure. Engineers and technicians described working with determination and ingenuity to overcome material shortages. They improvised solutions when standard components became unavailable. They maintained equipment under impossible conditions with inadequate tools and spare parts. Individual effort and technical cleverness could not compensate for systemic disadvantages in industrial capacity and resource availability. Major Nobuo Fujita, who had directed radar operations at Yokosuka Naval Base throughout 1944 and early 1945, described the progressive degradation of radar coverage as the war approached its end. Equipment that initially functioned adequately deteriorated rapidly. Vacuum tubes failed with increasing frequency. Replacement parts arrived slowly or not at all. By March 1945, we could maintain perhaps half our radar sets in operational condition at any given time. Operators learned to work around equipment limitations, but there were limits to what skill could overcome. The psychological impact on Japanese radar operators mirrored the experience of their counterparts in other technical specialties. They understood they were using inferior equipment. They recognized the technological superiority of Allied forces. Yet they continued performing their duties with professionalism because abandoning those duties meant abandoning their comrades to even greater danger. The knowledge that their radar systems provided inadequate coverage did not eliminate the obligation to provide whatever coverage was possible. This dynamic created a peculiar situation where Japanese radar personnel simultaneously understood their technological inferiority while maintaining operational capability within the constraints they faced. The examination of captured Allied equipment had stripped away any illusions about technical parity. Japanese operators knew exactly how much better Allied radar systems were, because Japanese engineers had studied those systems in detail and explained the differences clearly. The captured SCR-270 that Lieutenant Commander Takahashi examined on Corregidor in May 1942 had traveled a strange path after its initial analysis. Shipped to Tokyo, examined by multiple teams of engineers and technicians, partially disassembled for detailed component study, it eventually ended up at the Navy Technical Research Institute, where it served as a reference standard for radar development efforts. Engineers working on new Japanese radar designs could compare their prototypes against the American system, a constant reminder of the performance standards they were attempting to approach. By 1945, that same SCR-270, now 3 years old by Allied standards, still represented a performance benchmark Japanese radar developers struggled to match consistently. The system that had been cutting-edge, American technology in 1941 remained superior to most Japanese radar systems deployed in 1945. This static comparison illustrated how completely Japan had failed to keep pace with Allied radar development, despite possessing captured examples to study and reverse engineer. The strategic bombing campaign's final months demonstrated the ultimate consequences of this radar inferiority. American B-29 seconds flew with near impunity over Japanese cities. Radar-directed anti-aircraft fire proved ineffective against aircraft flying at altitudes exceeding 25,000 feet. Fighter interceptions succeeded occasionally through individual pilot skill and determination, but systematic radar-directed defense proved impossible with the equipment available to Japanese forces. When Japan surrendered in August 1945, American technical intelligence teams examining captured Japanese radar equipment reached conclusions similar to those Japanese engineers had reached 3 years earlier when examining captured American equipment. The Japanese systems demonstrated competent engineering within severe constraints. They reflected intelligent design choices given limited resources. They were hopelessly outclassed by current Allied radar technology and represented capabilities Allied forces had surpassed years earlier. The irony was not lost on the American teams. Japanese engineers examining Allied radar in 1942 had understood immediately that they faced a technological gap that would prove impossible to close. American engineers examining Japanese radar in 1945 reached the same conclusion from the opposite perspective. Both groups recognized they were looking at equipment that reflected different industrial and organizational realities more than different levels of scientific understanding. The captured radar sets told a story that transcended technical specifications and performance characteristics. They embodied the material and industrial realities that shaped the Pacific War's outcome as surely as any battle or campaign. Japan entered the war with scientific knowledge comparable to its enemies, but lacked the industrial foundation to translate that knowledge into deployed capability at the scale modern warfare required. Lieutenant Commander Takahashi, kneeling in the pre-dawn darkness on Corregidor, examining that damaged SCR-270, had held in his hands the physical proof of Allied technological superiority. The report he filed after completing his examination documented that superiority in precise technical detail. The knowledge gained from his work informed every subsequent Japanese radar development program. Yet knowledge alone could not bridge the gap between what Japanese engineers understood was possible and what Japanese industry could actually produce. The examination of captured Allied radar had answered questions about enemy capabilities. It had raised more troubling questions about Japanese limitations that would remain unanswered until the war's bitter end, when surrender finally made those questions moot. The radar equipment captured at Corregidor served Japanese technical intelligence well, providing detailed information about Allied capabilities and design approaches. That information shaped Japanese radar development throughout the war. But information, however accurate and detailed, could not substitute for the industrial capacity and organizational effectiveness that radar deployment at scale required. Japanese engineers learned what the enemy possessed. They learned it early enough that, in theory, countermeasures might have been developed and deployed. In practice, the constraints they faced made effective response impossible, regardless of how clearly they understood the problem. The story of Japanese radar development during World War II stands as a case study in how technological warfare rewards not just scientific understanding but industrial capability and organizational effectiveness. Japan possessed talented scientists and engineers. It achieved early progress in radar technology that suggested potential for competitive development. That potential went unrealized not because Japanese personnel lacked skill or determination, but because the foundational requirements for modern technological warfare extended beyond individual technical competence. The examination of captured Allied radar equipment provided Japanese engineers with a clear-eyed assessment of enemy capabilities and their own limitations. They used that knowledge as effectively as circumstances permitted. Those circumstances, shaped by industrial capacity and resource availability more than technical understanding, determined that even comprehensive knowledge of enemy technology could not enable effective response when the underlying material conditions made matching enemy capabilities impossible. In the end, Lieutenant Commander Takahashi's examination of that damaged SCR-270 on Corregidor provided answers that Japanese forces did not want but needed to hear. The Allied technological superiority his report documented was real, substantial, and beyond Japan's capacity to overcome through determination alone. Understanding that reality did not change it, the radar war, like so many other technological competitions during World War II, was decided not by who understood the technology first, but by who could deploy it at scale with reliability and effectiveness. In that competition, Allied industrial and organizational superiority proved as decisive as any tactical victory won through radar's direct application. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.